Now let's begin the set theory with defining a set. As we know, set is a well-defined collection of objects. So for example, the set of 7 days of a week, or the set of all natural numbers, and so on. Now here there is no ambiguity as to what are the 7 days of a week or what are natural numbers. So therefore it is clearly defined. Now on the other hand, if we consider some collection which is defined as, say, the set of 10 best batsmen in the world. So everyone will have their own different opinions as to which 10 batsmen should be called as the best. So therefore that collection will not form a set in mathematics. Alright. Now sets are typically denoted by uppercase letters, as we will see in various examples ahead. Also, the two methods to describe a set are roster method and set builder method. Now let's see the details of these two methods. The roster method is that in which all elements of a set are listed down within braces and they are separated by commas. So here is one example of set P, which consists of elements 10, 20, 30, 40 and so on up to 100. So we can see that they are the multiples of 10, first 10 multiples of 10. Now there is a note here that order of listing the elements is not important. So it does not matter if we write the same elements as shown here. If we write them in a different order, then that does not form a different set, but it is the same set, because we can visualize a set as a kind of, say, a team consisting of people, and when we say a team, the order is not important. So therefore this point should be kept in mind. Now the drawback of this roster method is that if the set is very big, that is it contains large number of elements or maybe even infinitely many elements, then it will be obviously not worthwhile to list down the elements themselves. So therefore we use a more compact and elegant method, that is a set builder method. Now in this method, a general property or a rule which can be used to refer to all the elements of the set is mentioned. So rather than mechanically listing all the elements, we try to find out, is there some general formula or general property that applies to all the elements together and that can describe all the elements. It's a kind of a generator function. So as an example, let us see one set A, and the way we read it out is A is a set of all such elements X such that, this colon means such that. Now how is X? Now X is such that it can be written as 10n, that means it is 10 into n, where n belongs to capital N. That means we know that n is a natural number, but n is also less than or equal to 10. So that means n is a natural number which is less than or equal to 10, and taking this n, if we consider 10n, then that gives us a particular value of X, and the set of all such possible values of X is set A. Right. Now the another way is, instead of colon we can also write slash. So some authors or some books also use this notation, and instead of writing n less than or equal to 10, we can equivalently write that as n less than 11, because if it's a natural number and it is less than 11 means maximum it will go up to 10. So in set builder method we can have a bit of a liberty to write the same set in slightly different ways. Now let's go ahead and see a small point which we have already seen. Now this is a symbol of X belongs to A. That means we write X epsilon, which is a Greek symbol. So X belongs to A means X is a member of set A. If X does not belong to A, then we write in this way. Right. Now let us solve a few sums, but before that we have to review the different number systems once again, although we are familiar, but it will be good to just have a look at them once again. Now the natural numbers is a set of the numbers 1, 2, 3, that is a basic counting numbers that we learn when we learn to count. that is denoted by capital N. Then the whole numbers denoted by capital W. They are nothing but the set of natural numbers plus additional element 0. Alright, so that makes it the whole numbers. Now integers are as denoted here. They are unending on both the directions, that is plus and minus, and some of the sample elements in between are -3, -2, -1, 0, 1, 2, 3 and so on. Next we have the rational numbers, typically denoted by Q. Now they are the numbers of the form P by Q, where P and Q themselves are integers and Q is not equal to 0 because Q is in denominator. And when we say P and Q are integers, the P by Q is also called as a fraction, so that P and Q can also be termed as co-prime to each other. That means there is no common factor between them, because if there is a factor then we can definitely cancel out and get some pair which is co-prime. So that is a rational numbers. Now irrational numbers, they don't have a different definition, but it is just that the numbers which are not rational numbers are irrational numbers. And of course both rational and irrational together form what is called as the real number system. So real numbers are nothing but the numbers which can be plotted on a real number line. So that is a simpler approach to understand real numbers. Now let us solve few sums based on the roster method and set builder method. Describe the following set by roster method. So here if you see, we are given a set in set builder notation. Set A is a set of all elements x such that x is equal to n square plus 1, where n is a whole number and n less than 5. So if you see, n is a whole number and n is less than 5 means it will start with 0 and will go up to 4, because that's the only allowed value of n. Now with this n we generate x, so therefore A will be nothing but, when we have n equal to 0, you put 0 square plus 1, that gives us 1. When you put n equal to 1, we have 1 square plus 1, that gives you 2. When we put 2, we have 2 square 4 plus 1, which is 5. For 3, we have 3 square plus 1, which is 10. And for 4, we have 4 square plus 1, which is 70. So in this way we have listed down the set in roster method, right? Let's go to the next question, in which we do the reverse operation, that is describe the following set using set builder notation. Now here if you see, we are given the individual elements of the set, and if you see, there is a dot 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 at the end, so it indicates that the set is unending, that is there are infinitely many elements in that. So how can we describe all these elements by some common pattern or a common link? For that, let's first observe the elements given. If you see, all the numerators are natural numbers, whereas if you see the denominators, they are also natural numbers, but they are odd natural numbers. They are the odd numbers. And if you see the first number, it will also have the denominator as 1, so it completes the link of denominator also, that is it's the set of all odd numbers in the denominator. So how can we write an entire number with a single notation? Okay, so for that, let us generalize like this. If we indicate the numerator as say n, right, then the denominator will be the nth odd number, isn't it? So if we see, when say numerator is 1, what is the first odd number? That is nothing but 1. When we have numerator as 2, what is the second odd number? That we know that it is 3, and so on. We can see that numerator is 3 and third odd number is 5. So going on in this way, in general we can consider the numerator as say n. Now in that case, how do we describe nth odd number? We know that nth even number will be 2n, but n odd number will be 2n minus 1. Okay, so therefore whenever you have numerator as n, the denominator should be it's 2n minus 1 because that is the nth odd number. Alright. So therefore here we describe the set as the set of element denoted by 2n minus 1 such that n is a natural number. That's it. Now there is no restriction on what value this small n can assume because it can be any natural number, as we see that the collection is unending. Right. So therefore in this way we have described the given set using set builder notation.